All right, here we are again for part 2. Okay, so we're going to move right along. So next we're going to look at shear and bending moment functions. Shear and bending moment functions. In the previous example, we learned how to get shear and bending moment for a particular condition, where I was asking for the shear and bending moment at one particular point in space, where I said, what is the shear and bending moment just at this one point C? But what if I want it at any point along a member? What if I want it as a function of x? So let's see. Shear and moment functions. Key. Cut at x. In other words, when you draw your free body diagram with a cut in it, the x is right at the cut. Keep origin constant. Do not restart your x at different values. 0 should always be, for example, from the left side of the beam, which is usually the most convenient. Okay? When do I need a new free body diagram? Essentially, when the load changes. Or could be better said as a discontinuity in the load. For example, a distributed load stops or starts. Stops or starts. A concentrated force, if you have a concentrated force, that is an instantaneous change in the load. Concentrated forces, concentrated moments. Supports, etc. Essentially, anywhere where there is a discontinuity in the load, when you're developing a moment function or a shear function as a function of x, you are going to need a new cut. So we'll work through that. Okay, let me work through another example. Oh, did you all get the previous page? Oh, sorry. I know this is a lot, but you have a weekend to study it, thankfully. So we'll talk about it a bit more on Monday. But this is it's just kind of, I like to normally spread out shear and moment over quite a bit of time, but the nature of just the nature of a summer course, it's all crammed together. Okay. Example 2. Also sometimes pronounced as exemple by some folks, perhaps. Example 2. So let us say I have another beam that is supported like this. So not quite a simply supported beam. It's actually a simply supported cantilever beam, like this. Say I have, again, a x, a y, and let's call this cy. cy. And the forces on here I'm going to have a distributed load, which is a load that is uniform across the member, or it's basically a load that is at a certain pounds per foot. So say 2 kips per foot. This means that every foot along the beam there is a 2 kip load. And then at point B here, there will be an external moment applied of 36 kip feet. So we have an external moment at B. So essentially the loads applied to the structure are the distributed load and this 36 kip foot couple at B. This is B, this is A, this is C, and we'll need some dimensions. Our dimensions are going to be 9 feet from A to B, 9 feet from B to C, and 6 feet from C to the end of the free end. And X is going to start from the left and increase that way. So we are asked to find the shear and moment diagrams. Find V and M diagrams for this beam here. Find V and M diagrams. All right, so solution. We'll see this a bit more when we talk about centroids. But remember when we talked about replacing a set of point loads with an equivalent load at their center? Remember that stuff? A lot of you were confused by that, but this is the point where you really need to be aware of this stuff. So the first thing I'm going to do is find a reaction. In order to do this, I need to recognize that a distributed load can be replaced by an equivalent load at that load's centroid. Okay? A distributed load can be replaced by an equivalent load at that load's centroid. So here, 2 kips per foot, and the total length is 24 feet. So we'll look at, so in other words, to find the total load from this distributed load, it's going to be 2 kips per foot times a total of 24 feet, so 48 kips. And that would act, the equivalent load for the only for the purpose of finding reactions is at the center here. Sum of moments about A is 0, which equals 36 kip feet minus 2 kips per foot times 24 feet times 12 feet. Okay, what is this? Actually, let me finish it off, and then I'll 18cy equals 0. Okay, this is a sum of moments about point A. The 36 kip feet is a couple. Again, if you ever find yourself writing a moment arm length next to something that's labeled in kip feet, you know you're doing something wrong. This is a couple. This is a point moment. It doesn't have a moment arm. It already has a moment arm baked into it. This is a couple. If you sum moments about any point, it will generate a 36 kip feet moment about that point, as we discussed when we discussed couples. A 2 kip per foot, this whole expression here, this is the moment about A generated by this distributed load. We're taking first we're finding the total load of this, which is 24 feet times 12 feet, and then 24 feet times 2 kips per foot. That's the total value of all of this put together. And then the equivalent distance from A, which is 12 feet. So in other words, like this. It's like we're saying we're replacing this with a 12, 2 times 24. 2 times 24 at a distance halfway across the beam. We're replacing it with an equivalent point load, only for the sake of finding reactions. Again, can replace distributed loads with equivalent point loads in order to find reactions. To find reactions.
So the little term is the equivalent point load term?
Well, this part here, and then times the moment arm distance of 12 feet. And then all of this will lead to Cy equals 30 kips upwards. So we have that reaction here, Cy, and then simply sum of forces in the y direction equals 0, equals negative 48 kips. That's this stuff here, plus Ay plus 30 equals 0, and this will lead to Ay is 18 kips upward. And so those are our reactions, Ay and Cy. Now, we need to talk about how many cuts we're going to need to make. This system has a series of discontinuities in it. This system has a series of discontinuities. I'm looking at this and I can see, again, remember what I said, to find reactions. This is key, to find reactions. We will only use the equivalent point load method for finding reactions and for nothing else. Okay? So when we actually make cuts, we're not going to use the equivalent point load. We cannot simply, a point load acting at a point. In other words, 48 kips acting at the center does not generate the same shear and moment as a distributed load across the entire beam. It does generate the same reactions as a 24 kip or a 48 kip point load at the center, but the shear and moment will not be the same. But anyway, we're going to need to actually take 3 cuts, one from A to B, one from B to C, and one from C to the end. And the reason for that is because each of these has a discontinuity. At B, there's a discontinuity, which is the point moment. From B to C, let's see, at C, there's another discontinuity, which is the reaction. And then, so there we have it. We have 2 discontinuities. We'll need 3 sections. How many cuts? This beam has 2 discontinuities. Therefore, we will need 3 sections. 3 cuts. One from, we'll have to do from, in the end what we're going for, we're going to get something like this. We'll get like a v of x is a piecewise function, something, 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 one where x is less than or equal to, maybe x is less than 9 feet, one x is between 9 feet and 18 feet, and another where x is greater than 18 feet. That's what we're going for here. That's what I mean by discontinuities and sections.
No x less than or equal, or
Ideally, it should be the same. Ideally, it should be the same. Although, if you have a point load, it can sometimes cause a jump in the shear. But anyway, but I wouldn't be concerned too much about the discontinuous point. Okay. All right, any questions on this so far? That is an external load. It's literally like I'm coming along with a big old wrench to this beam and torquing it. It's an external force, just like a load on the beam would be. It's an external load. Okay, so first I'm going to do a cut at x when x is less than 9 feet. I'm going to draw a free body diagram showing what this looks like when x is less than 9 feet. So let's consider that. Let us consider that beam. Well, what would that look like? Well, I would have my same reaction at A. This is A here. And I would have 18 kips here. I would have my distributed load that's still all the way along here. That is 2 kips per foot. And I'm going to have some Vx and Mx. I'm ignoring the N because it's going to be 0 clearly. And the dimension here is simply x. Like this. So this is the left end of the beam. I am cutting it somewhere between here and here. So we're not including the exact point at B, so that moment won't show up there. But we're drawing a free body diagram, a generic free body diagram of some point between those two, between 0 and 9 feet. And now we simply we simply do a sum of forces and etc. Now again, remember, we're going to always draw our moment and shear with a positive sign notation. And if we get negative, well, that means that that's negative at that point. Okay. So the shear will be the easiest to get. Sum of forces in the y direction is equal to 0. Thus, we'll have 18 kips minus 2 kips per foot times x. Consider this. What this is saying is each foot of beam has 2 kips of downward load applied to it, and there's x feet of beam on this free body diagram. Therefore, the total downward load will be 2x. Minus Vx equals 0. And therefore, we can see if you solve for V of x, or Vx, is equal to 18 kips minus 2x. If I do a sum of moments, let's see, a sum of moments about x, I think. Let me double check this here, negative x. Yes, okay. I'm going to sum moments about x here. I'm summing moments about the left end. Or sorry, the right end. I'm summing moments about this point here. 0. I'm going to have negative x times 18 feet. Or sorry, 18 kips. This 18 kip is generating a negative moment about point x. Plus, now this is where it gets a little funky, 2 kips per foot times x over 2. Oh my, what is this nonsense? Okay, what this is the moment generated by this distributed load about point x. See, the total load, if we find an equivalent load of this piece right here, it would be a total load of 2 times x, and it would occur at x over 2. It would occur halfway across the beam. In other words, I can show a sort of an equivalent point load of, the equivalent point load here is 2x, and the distance is x over 2. the equivalent point load of this distributed load. All right, and then plus mx is equal to 0. And then if we solve for mx, we will get that m of x is equal to 18x minus x squared. Do you notice anything with this? Well, it's quadratic, that's true, but look at the relationship between this and this. Yeah, there's clear that is not a coincidence. Now maybe it's just coincidence, maybe, but no, I can tell you it is not a coincidence. This is actually true. There is a derivative relationship. Shear is the derivative of moment, and actually your distributed load is the negative derivative of shear. So if we have a downward distributed load of 2 kips per foot, it's the derivative of this. And we'll see that later on. We're doing the non-derivative method right now, not applying calculus techniques, but we'll see that later. Okay, so that's one cut. Yes?
So your second equation, finding the moment about x, x being any value we choose between 0 and 9.
Yes, we're doing a sum of moments about x, where x is any arbitrary value between 0 and 9.
But then why do we presume that the distance between that arbitrary moment is x divided by 2?
Because what this is saying is this is the equivalent load of however much load is to the left of where you've cut. So in other words, what this is saying is that if you cut at 3 feet across, or say if you cut at say like 6 feet, there will be 6 feet here, and so there'll be an equivalent of 6 times 2 or 12 kips halfway down at 3 feet. So it's all defined. We basically construct this defining everything in terms of x. We have to construct this defining everything in terms of x. Okay. Now we need to make another cut. So this I could I'll put some step numbers on here. This is step 2. This is step 1, reactions. And then step 3 is going to be another cut. Cut at x when x is greater than 9 and less than 18. So again, we're going to still include everything from the left side of the beam. So this one's going to be a bit more involved. You're like, no, not more involved. Okay, so I'm going to have my 18 kip force here. Actually, let me label some points first. Let's say I have A, B, and that'll do it. And I'm going to have the same 2 kip per foot point load, or sorry, 2 kip per foot distributed load all the way down the line. And then, let's see here. I'm going to have a V of x and an m of x. And then at B, I will have a 36 kip foot point moment. But I will not have the reaction yet. The dimensions from A to B is 9 feet. And this dimension here, well, I don't actually need that dimension. That's okay. Well, actually, let me think about that. No, that's still okay. That's 9 feet. And this would actually be like 9 minus, or x minus 9. Let me show you. I will show you. I want to show you where x is. X minus 9 from here to the end. And this entire thing is x. Yes.
Why did we include the 36 kip feet in the first?
Because we were cutting somewhere between A and B. We were cutting somewhere between A and B, but we don't try to include, we never make a cut right out of discontinuity. We cover some point in between, okay? So,
Sorry, it's x minus 9 from B to where x is.
yes. See, this dimension here would be x minus 9. I don't know if we'll need that, but there we have it. Okay, so I think that's it as far as what we need. Yeah, that's good. Then I'll do the sum of forces in the y direction is equal to 0. And from this, we will get that 18 kips minus 2 kips per foot times x minus v of x equals 0. So shear as a function of x is going to be 18 kips minus 2x. And then summing moments, again about point x, I will get negative 18x. This is the moment produced by this reaction at the left, plus 36. That's just the 36 kip foot point moment, plus 2x times x over 2, same kind of thing as before, the equivalent point force of all of this stuff here, the distributed load, and it's applied at its centroid, which is halfway across our section, plus m of x. And if we solve for m of x, we will get that m as a function of x is equal to 18x minus 36 minus x squared. And I'll let you copy that because we're going to go to one more cut and then we'll summarize everything. What do you think? I just see a bunch of people shaking their head and shaking their head with eyes just wide, going, "Oh God, what did I get myself into?" Okay, yes.
About 15 seconds behind you. Could you say how you got the moment about x again?
I took them some moments. Sorry. Okay, sorry. Some of moments about X again. This one here. Okay. Sorry, I just gave a smart aleck comment. Anyway. Okay. So let me just walk through this again. I want the sum of moments about this point here, about point X, for lack of a better word. 18. The 18 kip reaction is going to generate a negative moment about that point. The 36 kip feet point moment, it of course does not have a moment arm because it already is a moment. We'll just add a 36 kip foot moment there. And then the distributed load, all of this 2 kip per foot distributed load, let me actually label the 2 kips per foot on there. 2 kips per foot distributed load. All of this is going to, the total load of this is 2 times x. So if you had 12 feet or something like that, there would be a total of 24 kips there. And the average location of that, the centroid of that, is going to be at x over 2. Again, you can use this for the purpose of finding external reactions, essentially. Okay, yes?
How would I know that I chose the wrong direction for the shear or the moment? Is it would be negative?
Okay, how would you know if you chose the wrong direction for the shear in the moment? Well, if I'm cutting a beam like this and I have a cut that is on the right side of a member, I'm always just going to draw the moment as counterclockwise and the shear arrow as downward because that's positive shear. That is positive shear. And then if we have something, if we go and get a negative number, then we actually have negative shear, and that's it. So there really is no right or wrong. Just draw it assuming positive shear, and if you get a negative number, you have negative shear. Okay. Can I move on? Okay. All right. Then finally, we have one more cut to make. So again, let me summarize. The first cut was between A and B. We had to stop there because we had discontinuity here, which was the point moment. Then we just took our cut between B and C, And we had to stop here because our discontinuity was the reaction. It was a point force. And then finally, we'll need one more cut, which will take us between C and the end of the member.
So we did not include that reaction in this one.
Yes, we did not include the reaction in the last one because it was at the discontinuity. And then step 4, cut at X. For when X is between 18 and 24, 18 is less than X is less than 24 feet. And so we're going to have this beam here. And let me label some points and dimensions and forces, and I'll go a little crazy. Okay. A, let's say B and C. Draw my loads in red. Here. Nice distributed load. 2 kips per foot. And V of X and M of X here. I have a 36 kip foot moment here, 30 kips here, and 18 kips here. And that's all the loads, and then dimensions I'll write in green. 9 feet from A to B, 9 feet from B to C, and then from our cut at X to C is going to be a distance of X minus 18. And X, again, as always, is just an arbitrary coordinate from the left. Okay, so time to work through the equilibrium equations. So, sum of forces in the y direction, I will have 18 kips plus 30 kips. 18 kips is upward, 30 kips is upward. These are both of our reactions. Minus 2x minus v of x equals 0. And v of x is equal to 48 kips minus 2x, like so. So we have that. And then sum of moments about x. Sum of moments about x is negative 18x. That's the moment generated by the reaction over here, about point x, plus 36 from the point moment, minus 30, that looks like a parentheses, forgot my 0, minus 30 times x minus 18. That's the moment generated by this force here, this reaction here, plus 2x times x over 2, and that is the moment generated by the equivalent point force of this distributed load, plus m of x. And all of this is equal to 0. And m of x, therefore, is equal to negative x squared plus 48x minus 576. And that's the final moment there. So I can summarize all of this and say v of x, here, let me just combine all this stuff together. V of x is going to be equal to, you don't necessarily need to write the summary, but I'm just going to summarize it here. V of x is going to be equal to 18 kips minus 2x for when x is less than 9 feet. And it's going to be equal to let's see, 18 kips minus 2x again. It's actually the same. For x is greater than 9 feet, is less than 18 feet. And actually, it might be strange. It might seem strange. Why are we having a different one why is it the same here but a different range? And the reason it's the same is that this distributed moment doesn't actually affect the shear. It's a moment. It's not going to affect the shear at all. Discontinuities and load definitely will affect shear though.
Could we skip it?
We could combine them together, but we can't skip it when we make our cuts because the moment will exhibit a difference, as you'll see in just a second. And then finally, 48 kips minus 2x. Notice they all share that same 2x. For when x is less than 24 feet, is greater than 18 feet. Then m as a function of x is also a piecewise function. And it is, let's see here. Thank you, yes, 18x minus x squared for x is less than 9 feet. And then 18x minus 3x minus x squared for x is between 18 and 9 feet. And then it's going to be negative x squared plus 48x minus 5. That looks bad. Oh, there we're good. Minus 576 for x is less than 24 feet is greater than 18 feet. And now we have the full shear and bending moment expressions for this beam as a function of x.
Question. So I noticed each time you don't say less than or equal to, you just say less than. What happens at the points?
At the points, there's discontinuity.
Okay.
At the points, there's discontinuity, yeah. And eventually we'll get to the point of actually drawing shear and moment diagrams, and it will literally just jump. It's a piecewise function. It will just, well, let's see here. Does this come to be the same thing? Well, this one does, yes, but let's look at here. Let's see. At 18 feet, what does this give us? 18 minus 2 times 18 is negative 18, right? So negative 18. 48 minus 2 times 18 is 12. See, this shear diagram is actually just going to leap. It's going to jump. If I draw the shear diagram here, it's going to look something like this. Okay, it's going to start out as at negative 18. Or actually, sorry, positive 18. It'll start out something like positive 18 here. Positive 18. Then it will decline down at a function 2x. So at 18, it's down to, what was that, negative 18, right? So then it's down to, at some point it'll cross the x-axis. Then we'll have negative 18 here. Then it will jump up, literally a discontinuity. It will leap to 12, and then it will resume its linear decline until it's 0 at the far end. So yes, and the reason you might be surprised, like how can you have, you might ask, how can you have a discontinuity in a function like that? Well, the reason is because, remember how we talked about how point loads really can't exist? Well, this is why. This is why a true point load really can't exist, because then you end up with a discontinuity in the shear and moment. Now, that's fine for our models. It's for again, as a way of designing beams, this works perfectly well. But in reality, what this thing would actually do, if we get more toward real behavior instead of idealized behavior, it would do something like this. It would probably, exhibit more of a curve. So maybe it goes up like that, and then then it goes down, and then maybe it curves up slowly and then comes back down or something like that. It definitely, in reality, it would be a smooth curve in the actual, if you could measure it very precisely. But because in reality, physically, this 30 kip point load, what would that be? That would probably be like a big steel big steel column or a concrete pile or something like that, this 30 kip point load is probably, you know, transferred through an area that's, you know, half a foot across, 6 inches, a foot across, depending what whether it's steel or concrete. It takes a good dimension just to transmit that thing. But we're modeling this as a knife's edge, 0-dimension force. But whatever, that for beam design, that's fine. That's why we can have discontinuities in equations, because we're taking physical systems and modeling them with certain idealized models. Okay, moving on. We're not done yet.
13 slides are not done.
We're not done yet. On shear and moment day, we go nuts. Okay. Oh, how far do I want to take this? Okay. So, let's see. How can I explain this well? There's that. Okay, actually, I think I'll need to go to this one here. I want to talk about the relationship between load, shear, and moment. The relationship between load, shear, and moment. We got at it here when we saw the derivative relationship, but now let's keep going. So, relationship between load, shear, and moment. Oh, you know what? I should probably, let me just go ahead and draw the moment diagram while I'm at it. Show you what this would look like for this one. This would go something like, so there's the M. Sorry about that. I missed a bit of my own notes. It's going to come up like here in parabolic behavior. It will have a peak of 81. Then it will instantly drop down to 45 as our function. If you work through the functions, you'll get this. Then it will parabolically decline again. I cannot draw a parabola to save my life. Parabolically decline until down here it's at negative 36. And then it will parabolically rise up to 0 at the free end. On a free end, both shear and moment have to be 0. Okay. But at a pin, they also have to be equal to 0. And we'll look at that more when we talk about shear and moment diagrams by inspection.
Are you going, like on the test, is it going to ask for a final diagram like you just drew?
What was that question? For the
The question was, will we actually have to create the graphs? Yes. That's why this lecture is titled Shear and Moment Diagrams. Huh?
But we won't have a graphing calculator. Oh my.
Need to know something about parabolas and their behavior. I assume you all took Algebra 1.
So, what,
Hmm?
did you just plug in the smallest x value to find the points?
We're applying the boundary values, essentially. See, this came from the 81 comes from putting 9 into this equation. The 45 comes from plugging 9 into this equation. And there we can see there's a discontinuity, a sudden instantaneous plummet in the moment because of this here. Okay. And actually we can kind of see, we can tease out a bit of the relationships here. So notice a positive moment is applied externally here, right? A positive moment is applied externally here at this point, but the moment actually decreases. And the reason for that is because this is the internal moment that must resist the external forces. So if you're applying a positive moment, it's internally there'll be a negative moment resisting it. So that's why the internal moment decreases. Okay. I know this is a lot. Go home, not right now, but go home, go through the notes, read through the book, watch the lecture on the YouTube, you know, just, it's all there. Okay. I know this is a lot very quickly, but It's the nature of the beast. Welcome to summer. Okay. So let us discuss the relationship between load, shear, and moment. Relationship between load, shear, and moment. And moment. Okay. So let's see here. There are two forms that we need to consider. First, v of x is equal to the negative integral of w of x dx, where w of x is our distributed load.
Is it the integral of the negative or the negative?
Same thing. We can always move the negative out. If
That's right.
if you remember your calculus class,
Okay.
someone asked if is it the negative integral or the integral of the negative. I was like, it's the same thing. Huh? Oh, w of x is the load function. For example, in the previous example, did I just really say for example in the previous example? In the previous example, w of x would have been simply positive 2. W of x would have simply been positive 2. Okay. Huh?
Function of x, though, wouldn't it be positive 2x?
As a function of x, no, actually, w of x here would have just been 2. It's a constant value function. Okay. So, or that's what I should do for the online class. I should just like maybe not for a class that I do the same one for both of them, same lectures for both. Maybe for like another online class, I should just like give all the lectures in like a crappy British accent or something, and then everyone's like really everyone's really always wondering what. Oh, never mind. Just a weird thought. Huh?
They might never meet you.
Yeah, exactly. Huh?
As long as it's an easy class.
Okay. Or a really bad Russian accent or something like that. Yeah. All right, the moment about just like an obviously fake Russian accent. That'd be amazing. Okay, w of x equals, we can also get this derivative relationship, dv of x dx. Now, we can sort of tease something out here. If you have the shear function, you can get the exact value of the load function. But if you have the load function, you cannot just directly get the actual complete shear function, because remember the fundamental theory of calculus? This simply says this will give you the integral of a derivative from point A to point B will give you the change in the original function. So the integral of, if you remember from, oh, actually, let me complete my previous thought before I move on to the next one. M as a function of x is equal to the integral of v of x dx, or v of x is equal to d m of x dx. Okay. Oh, also, let me give you another little note here. Note w of x assumed down. We're sort of usually our in terms of loadings on beams, the most loadings are most distributed loadings are usually downward. If you think of like a floor and the weight of objects upon it, things like that. So we define downward as positive. Yes. So yes. If you had a upward force, like a beam, like if there was a upward force on a beam, an upward distributed force, it would actually be an integral of a negative. So you'd end up with a positive shear. Okay. But the okay. So if you remember your fundamental theorem of calculus, you have something like this, right? The integral of f prime of x dx from a to b is equal to f of b minus f of a. This is one way to express the fundamental theorem of calculus, right? Remember that? So what this is saying is the integral of the derivative does not give you the actual value, or it's sort of like the delta f of x. It does not give you the actual values of the function. It gives you the change in the values of the function between those 2 points. So what that means is if we know the shear function and we take the integral of that, we do not automatically know the moment. See that the shear is the derivative of moment. So if we integrate shear, we do not directly get the moment. We get the change in moment between 2 points. We get the change in moment between 2 points. If we integrate the load function, we do not directly get the shear. We get the change in the shear between 2 points. And so we will actually need to apply boundary conditions, just like we do in other calculus problems, to solve for the actual values of the shear. So, all right. Let's observe this. Man, I'm just writing with all sorts of colors today. Man, I'm getting excited. It's just shear and moment diagrams. Okay. You got this? Oh, I saw one for scope. Okay. I'll wait. It just has like a button that can start playing like elevator music. Okay, good now? All right. All right, I have one example here that I want to work through, and I think that should probably do it. And then we have one other thing we'll talk about, getting them by inspection, but I'll save that for Monday, I think. You should be able to get through the homework just using these two. Also, the book may talk about method by also talks about by inspection, I think. Okay, so consider this for a moment. Oh. Okay, do I have enough? Yeah. Oh, okay. So, example, trace. So we have a beam. Let's let this be a simply supported beam with no horrible discontinuities. But our distributed load will now be a triangular load. Dun, dun, dun. Oh, I don't want that last thing. Man, this just keeps getting more complicated and complicated, more complicated. You're just like, what hell will she dream up next? Parabolic load? Yeah. You know, I once gave a student I was tutoring in for a calculus AP test. Do you remember like method of solids revolution? And so you have solids revolution, and then you have the related rates, like two fundamental calculus concepts, right? Related rates of change, like the classic one is like the ladder falling down the wall or something like that, or the conical water tank, right? Where you have that constant ratio that makes it easy. Well, I gave him a parabolic water tank. So you first have to find the function of it you first have to find the function of it, the volume as a function of x, using solids of revolution, and then you have to take that equation and apply related rates of change to it. So yes, parabolic water tanks are a lot of fun. I don't know why someone would build a parabolic water tank, but you can solve it. I think those use more. Oh, I don't know. Are they conical inside? It's an upside down water bottle parabolic. Sort of. Sort of? Okay, anyway, let's get this thing. Okay, we're really going off the rails here. So let me just show you I'll draw the reactions on here. AY, AX, and BY. we're going to have point B, oh, derp. We're going to have A on the left and B on the right. A on the left, B on the right. I should probably complete this thought up here. This is 4 kips per foot. So previously, so we still have a distributed load, except here it starts out at 4 kips per foot up here, or over on the left side, and then it decreases until you get to the right side, where it's 0. This would be a triangular load distribution, you could call it. And the total length on this is going to be, oh, let's say 18 feet. Now, would anyone happen to know where the centroid of a triangle is? Yes, it's a third. We haven't gotten to the centroids unit yet, so I'm not going to ask you to calculate centroids, but I would ask you to know that a centroid of a rectangle is at the middle, and the centroid of a triangle is 1/3 from its base. So I do expect you to know those 2 simple cases. So just remember that the centroid of a triangular load is 1/3 from its fat edge. So the centroid is 1/3. Yes? I'm going to have both of them on the exam. Yes.
How far up does the centroid go? Just curious.
It would also go 1/3 up, although the concept of up doesn't really apply to here, because it's not really a geometric shape.
The fat edge?
The big edge. I don't know what you're going to call it. The leg. Okay. It's sort of Friday. Okay. The total equivalent, the total load here is just 1/2 base times height. So 1/2, 18 feet, times 4 kips per foot. Give me a break. I'm not a math magician. Okay. Go call your math professors math magicians. See how quickly they get mad. Okay, and so this is going to be at 6 feet from the edge. I always love that term, math magician. Yes. Huh? The 1/2 is the area of a triangle. This is going to be the value of that equivalent point load, 1/2 base times height, and the location of it is 1/3. So it's located 1/3 from the left, and its value is the formula for the area of a triangle, 1/2 base times height. Or this is equal to 36 kips. So again, we can use this. We're not going to use this point load for finding internal shear and moment. All we're going to use it for is finding the reactions. That's it. So please put that in your notes somewhere that you only want to use that for finding reactions mainly. Okay, so first we'll find the, and we're told find V and M. Okay, so step 1, reactions. We'll do a sum of moments about A. It's equal to 0. And I'll do 6 feet times 36 kips. Plus 18 feet times by equals 0. And from this, I will get that by is equal to 12 kips upward. Then I will do a sum of forces in the vertical direction is equal to 0 equals AY. Oh, it's too far away to be a subscript. It looks bad. Okay. AY minus 36 kips plus 12 kips equals 0. And from this, AY equals 24 kips, also upward. 2. So we have our reactions now. And obviously, I could also say sum of forces in the x direction, just for any pedants in the classroom. Sum of forces in the x direction, although I don't like how that looks. For all you pedants out there, is AX plus 0 equals 0, therefore AX equals 0, because there are no forces in the horizontal direction. So we have our reactions, and the next step is to develop our load function. Okay, so we need a load function. We're going to apply the previous integral relationships we saw on the slide before this, but in order to do that, we need a function. We need a w as a function of x. We need w as a function of x. Now, on your exam, I'm not going to give you anything more complicated than a simple triangular load. That's probably the limit of what I'm going to ask you to integrate. So nothing, it's not going to be too terrible. No, parabolic or no hyperbolic, or, but that's the limit of what I'm going to ask you to do. No, I'm sorry. Okay, no calculus puns? Too tired for calculus puns? Okay. Okay. First, this is linear function, and I know a linear function can be found by y equals mx plus b. So, linear. Therefore, we need something y equals mx plus b. Hey, I took algebra. I know how to do this. The slope m is going to be negative 4 kips per foot times 18 feet, rise over run, equals negative 2 over 9 kips per foot squared. And the intercept b is going to simply be 4 kips per foot. So we combine this together, and w of x is equal to 4 minus 2 over 9 x. We have our w as a function of x. We had w as a function of x. And now we'll apply integral relationships. I cannot integral. It's been a long day. We will apply integral relationships to get the shear and the moment. Never mind me, I'm clearly drunk. Water's in the bottle. Okay. Okay. Next, we wish to develop the shear function. Shear function. So we know that v of x, v as a function of x, is equal to the integral of negative w of x dx. So now let's plug and chug. And we have, let's see, I'm just going to plug this in. Integral of negative 4 minus 2 over 9x dx, which is equal to x squared over 9 minus 4x plus a c. But I'm just going to go ahead and call this c1 because we're going to have another c for the moment later on. Now, we're going to need a boundary condition. Need boundary condition to find c1. Boundary condition to find c1. And that can be found at the left. At x equals 0, the left end, x equals 0, v is 24 kips. Whenever you have a support on the left end, the initial shear is going to simply be the initial reaction. As we saw in this example here, we had this positive 18 here. That reaction caused an instantaneous jump in the shear, so that's going to be one of our boundary conditions. So we could say V of 0 equals 24 kips. And then, let's see. So V of 0, yes? Could we have said that V of 18 is 0? Not necessarily, no. I would have to say it's actually negative 12 if I said at here. Because it's going to be negative 12 and then the reaction is going to cause it to bump back up. You'll see when I plot it. V of 0, if I just plug in x equals 0 into this, I'm going to get 0 minus 0 plus C1 equals 24. That produces that C1 is equal to 24 kips. So therefore, V as a function of x is equal to x squared over 9 minus 4x plus 24. And this is in kips. Okay, bear with me. We're not done yet. We still have to get the moment function and then plot it. Just need to get the moment function and we'll quickly sketch the graph. I'm on my last page of notes. Okay. You're like, finally, I'm dying in here. Okay.
I think you already mentioned it, but I think I missed it. How'd you get the V is equal to 24 kips?
Again, how I got the boundary condition that the V at x equals 0 is equal to 24 kips is that if you have, say, a pin reaction at the left side, it's going to have that the shear is going to start as the reaction value. Okay? Just like in this one here, we had an 18 kip reaction and our shear started at 18 kips. Oh, you got this here? Okay. For get the moment function. So we know that m as a function of x is equal to the integral of v of x dx. I'm trying to get through this quickly. Here, I'll let you get out of here. Equals the integral of the shear function, x squared over 9 minus 4x plus 24 dx, which is equal to x squared over x to the third x cubed over 27 minus 2x squared plus 24x plus C2. And the boundary condition is actually easier this time to explain. The boundary condition is that the m at x equals 0 is going to be 0. And that's because we have a pin there. Anytime you have a pin or a roller, the moment at that location must be 0. Anytime you have a pin or a roller, the moment must be 0. A pin cannot resist any moment, therefore the moment there has to be 0. And we can use that as a boundary condition. And if we apply this, m at 0 equals 0 minus 0 plus C2 equals 0, that leads us to the C2 equals 0. Therefore, m as a function of x is simply x to the third over 27 minus 2x squared plus 24x. And that is our moment function. And then all we need to do is sketch a graph, and we have the shear and moment diagrams. So give me a minute. I just need to sketch these graphs out, and we'll be done. Yes?
So we can get shear and load functions from moment.
Yes, exactly. If you have the moment function, you know everything about the beam. You can find its shear and its load just by taking the derivative. But if you only have the load, you cannot get the actual moment function without knowing something about the beam itself. If I just gave you that would be a great test question. I just give you a shear function, or just give you like a shear function, ask where the load and moment be, and the actual answer for moment would be like unsolvable or something. Okay, I'm not that mean, but Okay, I try to avoid trick questions on tests. Okay, can we move on? Okay. Finally, 5, graph the results. Plot results. So first I will plot the load, which is just, I'm going to plot these all above each other. So this is going to be my W, or my load. This is, I have the 24 kip point load here, the 12 kip point load here, and a distributed load that starts at 4 and slowly decreases. 4 kip per foot. Then I'm going to have shear. That's going to start off at 24. Now this is actually going to be parabolic. Kind of like this. Oh man, oh well, that's okay. Actually, no, never mind. That actually turned out all right. Negative 12. And this is, again, v as a function of x. This is v. And notation, notice this is positive, positive, and this is negative. So we're going to have, here, we're going to have the arrows going like this, and here we would have the forces going downward and upward like that. And then and we could solve for that coordinate there. I don't have that in my notes right off the top of my head. M then is actually going to be a third power equation, and it's going to increase along here and then decrease. Oh my gosh. Except not looking all janky, hopefully. Like that. A perfect curve. Okay. And then, so it's going to be positive the whole time. Something to note, the M max is where the shear is equal to 0. The M max is where the shear is equal to 0. Then I just have a few more notes here. Again, we see that dv of dx equals negative w of x. This is definitely the derivative of this. Or sorry, this is definitely the derivative of this. And dm of x, or dm dx, is definitely v of x. And then a few notes. Note, you still have to write new functions whenever the load changes. New functions if, oh my gosh. New functions. New functions if load changes. If load function changes. For example, by new boundary conditions like reactions, etc. And we do need to always keep your x origin the same. And that's what I got for today. On Monday, we can talk about shear and moment by inspection. The class here in Houston, you'll have your exam on Tuesday. The class in Tyler will have your exam on Monday night. So that will do it. If you have any questions, I'll be up in my office after this. Yes?
I was gonna get like homework on Monday, gonna give us this test.
Something like that. Yeah, I could do that.
I don't know if we can like do that maybe over the weekend.
What do you mean exactly? Like?
I mean like just add that homework, we
Oh,
send the main
Put the oh, you mean to put the solutions on the site? Is that what you mean? Put the solutions?
Yeah, like just
Okay, yeah, I'll see what I can do. Yeah.
Monday.
Okay, that's fine. Okay, so we'll look at that. If you have any questions, feel free to see me after class or my office hours. I'll see you all on Monday. Have a good weekend. Study up for the exam, and as always, thank you.